thing we could be curious about is how do we find out whether two groups are isomorphic. So means same number of elements and same structure up to renaming of elements. So let's see. We can have this question. So if we want to determine whether they're isomorphic, here we have some suggested approach. So there's some basic approach. So order size of the group should be same, and we should also check whether if the group considered groups are abelian or not abelian, commutative or not commutative. Number of elements of each other, that's the order, and then subgroup structure, number of subgroups of some order, and so on, normal subgroups, and so on. So if any of these things are different, then they're not isomorphic, because the structure has to be identical between isomorphic groups. So that's interesting. So we can check any of these things, and if we must make sure that they work out the same. We should compare the orders of elements. That means to what extent, so actually, what was meant here, order of an element is to what power you need to take it in order to get identity of the group, and order of the group is how many elements there are in the group. Well, compare element orders means if some group has some element of some order and the other group lacks an element of the same order, then they wouldn't be isomorphic. So even this part of structure must also be same. And some groups are completely classified. Okay. All groups of prime order are isomorphic to cyclic group of prime order. All right. Fair enough. And then groups of order 4 are either Z sub 4 or Z2 in direct product with Z2. And then 6 is either cyclic Z sub 6 or symmetry group S3. All right. So we should match it to what they call a known model. And then we can try to construct an isomorphism. So if the earlier tests are passed, then we can explicitly try to define a map. Pick a generator if cyclic, all right. But if not cyclic, we can do other things, and so on. And another thing we can do is use structure theorems for abelian groups. So find the theorem of finite abelian groups. We can break each group into products of cyclic groups and compare the compositions. So, here they say an example. Z sub 8 is not isomorphic to this product of Z4 and Z2. All right, fair enough. For small groups, because say the table, it just gives all the products in between the elements. So if the group is big, it's very inefficient to write it out. But for small groups, we can do that. So up to relabeling, it is tedious and rarely used beyond tiny examples, right? So if the group is small, it can be quite used nicely. Here we have some examples. So Z sub 4 with addition and 1i minus 1 minus I. So both have 4 elements, both are cyclic and have an element of order 4, and therefore they're isomorphic. All right.